Hello students and welcome to the lecture. So students, as we know that we are covering the surface tension, or you can say we had started this topic in the previous lecture, and that was our part 1. In this lecture we are going to continue with the surface tension, and this is going to be our part 2. In the previous lecture we had discussed some really important points for the surface tension. In this lecture we will continue with the same thing. I hope you have revised the previous lecture in the well enough manner before you have come for this lecture. As many times I have reminded you, that is for your own benefit. If you are doing this on the regular basis, the thing will be in your favor. If you are not doing this on the regular basis, the thing might be against you. Okay. In this lecture, basically, we will talk about the capillarity and angle of contact. So these two topics are going to be our point of discussion in this particular lecture: capillarity and angle of contact. But as usual, before starting the actual lecture, there is a small disclaimer that we are required to understand before we proceed further. So, the disclaimer is like, the images used in a slide deck are for educational purposes only. We respect the intellectual property rights of the original creators and owners of these images. If you are the owner of any of the images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Okay. Now let's begin with the topic of capillarity. So basically, what do you mean by the capillarity? To understand this, first we have to understand the capillary tube. Okay. So a tube of very fine bore is called a capillary or hair-like tube. The phenomena of rise or fall of liquid in a capillary tube is called capillarity. So the term capillarity in actual related with the tube called capillary, and it is a very fine bore tube that is known as the hair-like. And from its capillary tube, the capillarity evolved. How? So we could say, actually we use the tube to check out the rise or fall of liquid. Okay, whether the liquid is rising in that tube or falling in that tube. And this phenomena of rising or falling of liquid in a capillary tube, it's what we call as the capillarity. It is found that when a capillary tube open at both the ends is dipped in liquid, which wets the walls of the tube. The liquid rises up in the tube. So, for the rising up case, we could say when the capillary tube open at both the end, okay, and then it dipped in a liquid. So, if the liquid is able to wet the walls of the tube, then we call the liquid is rising up in the tube. Here you can see that this is the water, this is the liquid. Here you can say this is the capillary tube. So this capillary tube is actually dipped in the water, and when it dipped in the water, here you can see the walls of the capillary tube is actually getting wet. So here we could say that the liquid is rising in the tube. Okay. In the second case, on the other hand, when capillary tube dipped in a liquid and liquid does not wet the walls of tube, the liquid depresses below the free surface of the liquid in the container. Okay. So like here you can say in figure B, this is a liquid mercury and this is the capillary tube. Okay. So when we dip this capillary tube in the liquid mercury, here you can say the capillary tube is unable to wet the walls of the tube. And due to this, what is happening? The liquid mercury is actually fallen in the case of this capillarity. So here we have discussed some points. Let's revise them in a quick manner. First, to understand capillarity, we require to understand the capillary tube. Capillary tube is a tube with a very thin bore, also known as hair-like tube. Okay, and actually the tendency of liquid rise and falling in the tube is known as the capillarity. So To check out whether the liquid is rising or falling in the tube, we could do two things, and we could actually, you can say, examine the two things. First is when we dip the capillary tube in the liquid and liquid is able to wet the walls of the tube, then the liquid is rising. For this, we have seen that particular example. This is the liquid water, and now we dip the capillary tube inside that liquid water. Here you can say the liquid is able to wet the walls of the capillary tube. So we could say the liquid is rising. On the second case, if the capillary tube dipped in a liquid and liquid is not able to wet the walls of the tube, the liquid depresses below the free surface of the liquid in the container, and we called it as a fall of liquid in the tube. Here you can say this is the liquid mercury, this is the capillary tube. So when we dipped it, that was the level of this mercury, but after dipping down, that is the level. So we could say the liquid is actually falling in the capillary tube. Okay. It has been seen that the extent to which a liquid rises or depresses depends upon the radius of the bore of the tube. So up to which extent, like you can say, generally I have seen people who got confused here that the liquid and falling of the liquid in the tube, it's depend upon the radius of the bore of the tube. Generally people assume that, but this is not, you can say, right statement. Here, if you just read it again, that particular misconception that you having in your mind will be cleared immediately. And what is this? So we could say it is not actually talking about the rise and fall of the liquid. That will be happen obviously. Okay, the rises and the depresses of liquid is not controlled by the radius of the bore of the tube. Actually, what is controlled? The extent. Up to which extent the liquid will rise if it rises. Up to what extent the liquid will depresses if it's depresses. Okay, so the extent of rising or falling, that is actually depend upon the radius of the bore of the tube. The capacity to rise or depresses is not depend upon the radius of the bore of the tube. So that thing makes clear in your mind. Please make it clear in your mind so that you should not get confused whenever you go by these terms. So let's see how does the radius of the bore of the tube affects the extent of rising or depressing of liquid. So the narrower the bore of the tube, the greater is the rise or fall of the liquid in the tube. So in the beginning we have seen that capillary tube is the tube which having a very you can say fine bore. Okay, so if the bore of the tube is narrower, if the bore of the tube is narrower, then what will happen? Any liquid that could rise, that will rise at greater. Any liquid that could fall, that will fall at greater. Okay, so rise and fall will be greater for the liquid if the bore of the tube is narrower. Practical applications of capillarity, let's see them. Oil rises in cotton wick of a lamp through the small capillarities found by the threads of the wick. Like this picture you can see. So whenever you burn the lamp, or you can say diya at your homes, okay, so oftenly you use the cotton wick. Okay, first you pour the oil there inside that particular lamp, and then you put the cotton wick there, and then you take that out like this. Okay, so have you ever wondered like how the oil is getting supplied to the wick so that the wick is continuously burning? Because of the small capillarities that get formed by the threads of the wick. Like the wick, cotton wick, their threads actually forms a small capillarities, and these capillarities actually making the oil rise up to the top where the fire is going on. So this rise of the oil on the continuous basis makes the lamp and diya enabled to glow continuously. The tip of the nib of a pen is split to provide capillary action for the ink to rise. Okay, like if you have a look at the pen, okay, so tip of the nib of a pen, it also provides a capillary action by splitting so that the ink of the pen could be rise and that could be used to written down the things. A blotting paper absorbs ink by capillary action. Here you can see this is the blotting paper, and if you see that these blotting papers are having are different colors. This one red, this one yellow, this one blue. How? Because this blotting paper, you can say, dip down in the liquids of different colors. And when it dip down, actually, it's also provide the capillarity due to the threads and all. And because of the capillarity, the liquid started rising up in the paper. And because of the color of the liquid, the paper becomes red, yellow, and blue. So here also we can say the capillarity is being used. We use a towel to dry our body after the bath, which soaks water due to the capillary action. So after the bath, whenever you use the towel also having a small threads. These threads provide the capillary action and they absorbs the water from a body because they provide it for to the rise up. It is by the capillary action that water reaches every branch of a plant or tree from the stalk stem. Like you can say, have you ever wondered that if you are seeing any plant in front of you and if you poured a water in the roots of the plant, how does the water is reaching the other parts? For example, the stem, the leaves, the flower, even the fruits. How the water reaching all these parts? Have you ever wondered? This is actually happens because of the capillary action. Now you could see the roots act as a capillary tube and they provides the rising up of water. So water start rising up from the stalk or stem, and because of this rising, it is enabled to reach the different parts of the plant. So moisturizers rises in plant by capillary action. To avoid damping of mortar and bricks on account of rise of moisture by capillary action, damp proof materials used in the foundation of buildings. Because these also, you can say, absorbs the liquid and protects the mortar and bricks. Due to capillary action, water rises to the surface of the soil in the fields and get evaporated. To avoid this loss of water, the fields plot and the furrows are leveled to increase the size of the pores so as to avoid any capillary action. Earthen vessels used in summer to provide cold water because they absorb the heat by providing a pores in the earthen vessels that acts as in capillaries. Therefore, water oozes out, get evaporated by taking heat from the earthen vessel and cools the remaining water in the vessel. A sponge retains water on being dipped in water due to the capillary action. Because the sponge also provides the capillary action of rising up of water. Due to this, the water level rising up in the sponge and that retains the water even after getting it removed from the water. It is happening because of capillary action. Now, after finishing the capillarity, let's have a talk of the angle of contact. So we could say the angle of contact between a liquid and solid in contact is defined as the angle enclose the tangents to the liquid surface at the point of contact and the solid surface inside the liquid. It is noted by delta. The angle of contact is acute, less than 90 in the case of liquid. which weld the walls of the container. So the liquid which having a capacity or tendency to rising up in the capillary, like I told you, to wet the walls of the container. Okay, and if it is able to wet the walls of the container, which means that it could rise up. Okay, so the angle of contact will be less than 90 for these scenarios, and is obtuse when it is greater than 90. It is for the liquids which do not wet the walls of the container. So the liquids that depresses, for them it is obtuse greater than 90. The angle of contact for pure water and clean glass surface is 0. Therefore, in glass tube, the manicures of water will be exactly hemispherical. Here you can see this is hemispherical. For ordinary water and glass, the angle of contact is about 8 degree, while for mercury and glass, the value is 140 degree. It may be noted that for a given liquid solid pair, the angle of contact is same whether the liquid is contained in vessel made of that solid material or a rod of that solid material is dipped in the liquid. Angle of contact between a liquid and a solid surface increases with increase in temperature of the liquid. So if the temperature of liquid increases, then the angle of contact also increases and decreases on adding impurity to the liquid. If the liquid purity will be compromised, or we could say if we add the impurity to the liquid, automatically the angle of contact that stays between the liquid and the solid surface will be decreased. For a liquid solid interface, if the angle of contact is acute, then the liquid will wet the solid. The liquid will rise in the capillary tube made of such a solid, and meniscus of the liquid will be concave. In the case the angle of contact is obtuse, then the liquid will not wet the solid, as we had just seen. The liquid will get depressed in the tube. Okay. Meniscus of the liquid will be convex. Rise of liquid in capillary tube. Consider a capillary tube of radius r open at both ends and dipped into liquid, which wets the walls of tube. So the angle of contact for such a liquid will be acute, and hence the meniscus will be concave. Here you can see this is the concave. Let theta be the angle of contact and T is surface tension of the liquid. The height h to which the liquid rises in the tube is given by hp equals to 2t cos theta by rpg. Okay. This expression is called the ascent formula. So what do you mean by the ascent formula? Ascent formula is hp equals to 2t cos theta by rpg. It follows from the ascent formula that the height h to which a liquid rises in the capillary tube is inversely proportional to the radius of the tube, inversely proportional to the density of the liquid, directly proportional to the surface tension of the liquid. Note, the liquid for which theta is obtuse, cos theta will be negative, and the equation h equals to 2t cos theta by rpg predicts a negative value for h. Therefore, such liquids should get depressed in the tube. This is what we really observe when a glass tube is immersed in mercury or molten lead, because the mercury or molten lead is that particular liquid which is not able to wet the walls of the tube. So that's why they falls down or depresses in the tube. Rise of liquid in a capillary tube of insufficient length. If the length of the tube h is less than h, therefore when tube is of insufficient length, it is found that the liquid does not overflow. In a tube of insufficient length, the liquid rises up to the top of the tube and increases the radius of curvature of its meniscus to a value r dash, so that r dash into h dash equals to r into h dash. Therefore, smaller the length h dash of the tube, greater will be radius of curvature r dash of the meniscus, but the liquid will never overflow. Effect of temperature on surface tension. The surface tension of liquid decreases with the increase of temperature. As we know, in the previous lecture also we had discussed the same thing. When the temperature of liquid increases, the molecular force decreases. So that's why a molecule gets kinetic energy to separate from each other. And because of this separation, the surface tension decreases. For a small temperature differences, it decreases almost linearly. The surface tension of a liquid becomes zero at a particular temperature, called the critical temperature of that liquid. So with this, we have finished this lecture. It is requested to all of you kindly revise the facts and figures that all we have discussed in this lecture and keep yourself ready for the next lecture. With this note, let's end this lecture and thank you.